These notes are over mechanical waves. So waves are just vibrations or disturbances in space that transfers energy. So mechanical waves are special in the fact that they need a medium to pass through. Okay, so for example, a medium in the ocean would be the water. Okay, so the ocean waves need the water in order to pass along the energy. Okay, sound waves use air particles as its medium in order to pass forward the energy. So there are two types of mechanical waves. There's transverse and longitudinal. Okay, so a transverse wave motion causes the medium to vibrate at a right angle to the direction the wave is traveling. Okay, so if you were going to be creating a transverse wave, if you had a rope that was attached to the wall in front of you, you would move your hand up and down. So you would be moving the medium, which is the rope, up and down, which is perpendicular to the direction the wave would travel, which is towards the wall in front of you. Okay, so here I've just labeled the different terminology that we use for waves, and it's easier to kind of label the transverse wave compared to the longitudinal wave. But here we have wavelength. This is just the distance between two similar points. So in this case, I labeled between one crest and the next. Okay, its symbol is lambda, which is like an upside down Y, and its units are in meters. Okay, crest is the highest point above equilibrium, so this line here would be at rest, the equilibrium. Okay, and trough is the opposite. It is the lowest point below equilibrium. Period, which its unit is in seconds. Its symbol is a capital T. This is the time for one full circle. Okay, and note that frequency F is the inverse of the period. Okay, so frequency equals 1 over our period. It is measured in hertz. So for this, a period is one oscillation. Okay, the time that it takes for one oscillation. The frequency is the number of oscillations per second. Right, and then our amplitude is the maximum displacement at any point on a wave. So this would be the amplitude. It's the maximum displacement from equilibrium, or here would also be the amplitude as well, and it is measured in meters. A longitudinal wave motion causes the medium to vibrate in a parallel to the direction the wave travels. So we could demonstrate this if we had a slinky. So to do this, you would move the slinky back and forth towards the end of the slinky, okay, and this would cause these compressions and rarefactions to form, which is the transfer of the energy down the slinky. Wave velocity can be derived knowing that the velocity, the normal velocity equation is displacement divided by time. Okay, so for waves, the displacement of one wavelength occurs in a time interval equal to 1 period of the vibration. Okay, so velocity, which is in meters per second, is equal to the wavelength in meters divided by our period, which is given in seconds. Okay, and we just discussed how the period and frequency are related. So frequency is equal to 1 over our period. And so we could also use the equation velocity equals frequency times the wavelength. So velocity is in meters per second. Frequency is in hertz, and then wavelength is in meters. Okay, so we can use either one of these equations. It really just depends on the information that's given to you in the actual question. So for the example, a piano string tuned to middle C vibrates with a frequency of 262 hertz. Assuming the speed of the sound in air is 343 meters per second, find the wavelength of the sound waves produced by the string. So they give us frequency, they give us speed, and they want us to know wavelength. Okay, so the equation that would best fit would be this one, since it's giving us speed or velocity, frequency, and it wants to know wavelength. Okay, so I just plug in the information. 343 was my velocity, frequency was 262, and then I solve for my wavelength of 1.3 meters. Okay, the key thing is just make sure that all of your units are in the standard form before you plug in your information. We're going to continue on to wave interactions. So because mechanical waves are not matter, but rather the displacement of matter, two waves can actually occupy the same space at the same time. So this combination of the two overlapping waves is known as superposition. So there's two different types of superposition, and they're labeled as interference, and they can be constructive interference or destructive interference. Okay, so if we have a smaller wave approaching a larger wave that's going in the opposite direction, when they meet in the middle, they actually combine to become a greater amplitude. And then they're going to continue on their path where the smaller one is still moving to the right and then the larger one is still moving to the left. Okay, so this is an example of constructive interference. They're going to add together to create a greater amplitude. Okay, for this next one, we have a wave that has a displacement in the positive direction and then a wave that it has displacement in the negative direction moving towards each other. When they meet in the middle, they're going to cancel each other out and then continue to move on after that. So this is an example of destructive interference. And so we can actually use these properties of superposition in order to help with different technologies. So for example, if you've ever been in like a surround sound area, there's particular spots that the surround sound is going to sound even better because of constructive interference. So the place that you sit on the couch, the way that the speakers are pointed towards that direction is so that constructive interference happens so that you get the best sound possible. If you've ever tried on sound canceling headphones, like the ones you have to turn on to do the sound canceling, they actually use destructive interference in order to cancel out those outside sounds so that they don't enter into your ear canal. So basically what it does is it picks up the frequencies around you and it matches that, but in the opposite displacement in order to cause destructive interference so that you don't hear the outside sounds from the headphones. So what happens to the motion of a wave that reaches a boundary? When a pulse travels down a rope whose end is free to slide up the pulse is reflected from the free end. When a pulse travels down a rope that is fixed at one end, the reflected pulse is actually inverted. So here we have an example of a fixed end. Okay, so if we tied this to a pole, our rope to a pole, if I send down an impulse that is in the positive displacement, okay, once it hits that fixed end, it's going to reflect back, but it's going to be inverted and be in the negative displacement direction. Okay, if I have a free end, meaning that I just loosely tie this over so that the string can move up and down the rail, okay, as the wave comes forward, the loop is going to raise up and then drop back down and send back the reflected pulse in the same positive displacement as the beginning pulse. So when waves superimpose with reflected waves of a fixed boundary, it creates a pattern of waves that appears to stand in place. So this is known as a standing wave, okay, where we have areas of destructive interference and areas of constructive interference, okay? So when these if I continue to send a periodic wave down this string, the ones bouncing back would sometimes cause destructive interference and then sometimes cause constructive interference, okay? So it would create this pattern that we see here where it doesn't appear that the wave is moving, it appears that it's just bouncing back and forth or up and down in one place. Okay, so this spot here, the nodes, these are areas of destructive interference, and then we have these wide areas known as antinodes. This is where the vibration has the largest amplitude. So we will speak more on this, not in the next section, but the following section, kind of looking at the different standing waves and their behaviors. So for the practice problems, you will be doing questions 1 through 7. Just be careful, like for this question, a piano emits frequency that range from a low of about 28 hertz to a high of 4200 hertz. Find the wavelengths in air attained by this instrument when the speed of sound is 340 meters per second. So you're actually going to be calculating two things. You're going to be calculating the wavelength at 28 hertz and then calculating the wavelength at 4200 hertz. Okay, so just be careful, make sure you're reading through the question and understanding exactly what it's asking of you. And then also just make sure that all of your units are in their correct forms before you plug them into any of the equations.